Hello everyone, I'm Zhang from Anhui University. Our presentation title is Exploring the Individuality and Collectivity of Instance Behind the Interaction of Graph Collaborative Filtering. And this is a joint work done by the PhD Zhang and Dr. Lei Sang and Professor Yiwen Zhang. And firstly, I will introduce the recommender system and intent modeling. Specifically, the core of a recommender system is to predict whether a user will interact with a new item in the future. As shown in the figure on the right, the input of the recommender system is the historical interaction information, for example, the explicit or implicit feedback, while the output is the interaction probability of a user to a new item. The basic idea of the collaborative filtering is the recommendation system is the collaborative filtering, which assumes that the user with behavior similarity will show similar preference for item. Based on this definition, we can find that the interaction is crucial for the recommendation task. In fact, in practice, we can abstract the interaction between user and item into the bipartite graph structure as shown in the figure A. In fact, we can further refine the interaction between user and item by considering that the user's behavior is influenced by the intent. And the intent reflects the real reason why the user chooses an item, as shown in the figure B, which is an intent-based disentangled interaction graph. Okay, in this sense, we have the three user intents, C1, C2, and C3. So in that sense, we have the two attributes for the user side. For example, on the one hand, user's behavior is not isolated, but also influenced by others. For example, in fact, the user group U1, U2 like movie with horror themes suggests that the user's behavior is come from a collective intent C1, and the C1 means both of them like the horror movies. This phenomenon is also known as the bandwagon effect, which represents a common choice of a user group. On the other hand, user behavior also reflects the individuality. For example, the user U1 not unlike the horror movies, he also likes some action elements that is different from the user U2. Okay, for the item side, we could have the similar definition. Although items are not subjective, we can also define the item intent as an attribute for the reason to choose an item. As a counterpart, the item also has two attributes, named the popularity effect and the individual characteristics. And the popularity effect is affinity of item. The more popularity within a unique community, the more likelihood of it being selected. And the individual characteristics are the deeper reason for user's choice. Okay, so then in that sense, the interaction between user and item are influenced by both from the collectivity and the individuality, which can be abstracted into the causal graph showing the figure C. For the user side, we have the individual preference and the bandwagon effect. For the item side, we have the popularity effect and the individual characteristics. When we get a closer look at the interaction, we will meet some new challenges. The first one is how to consider both collectivity and individuality and realize adaptive trade-off. Second one is how to mold the user or item intents using sparsity and semantic implicit feedback. Okay, based on these two challenges, in the section 2, we will propose our solution called the bilateral intent guide the graph collaborative filtering called BIGCF for implicit feedback-based recommender system. Okay. Specifically, as we said before, consider the specific issue of implicit feedback. We need to reconvert the graph generation, a graph recommendation task into the graph generation task and include the feature distribution of user and items. Besides, we also need to take the intent into account, and the figure presents the complete framework of the proposed BIGCF is an end-to-end framework. Firstly, we need to include the interaction graph, and secondly, the bandwagon and the probability effect we said before are abstracted into the collective intents. The collective intents are shared parameters for a user and items, which represents key kinds of reason for user's choice. After that, subsequently, we need to construct the individual intent for each user and item to explore the individual preference and the characteristics. Okay, finally, we propose to graph contrastive regularization in both the interaction and intent spaces to get alignments and the uniformity for all nodes on the interaction graph. Okay. Firstly, as we said before, the concerning specific issue of implicit feedback, we need to include the feature distribution of user and item with approximate means and variance, both of the parameters of the Gaussian distribution. Okay. Next, we need to include the interaction graph by the light graph convolution to obtain the high-order connectivity between user and items, which is a common practice. After that, we can get the item structure embedding for user and item respectively, which represents the individual performance for user or the individual characteristics for item. This process is based on assumption that the user's behavior is consistent with the item that they have interacted with. For example, if a user buys lots of video game devices, we can naturally infer that he is a young student. The same conclusion holds true for the item side. Okay, after I get the structure embedding for user and item, we need to consider which collective intent is the main reason for user's choice. Okay, specifically, we first measure the correlation score between the structure embedding we learned and the collective intent we define. Okay, this process is based on softmax function and the inner products, and we calculate the probability for each collective intent. For the item side, we have a similar definition. After got the probability for each for the correlation score for all collective intents, we can construct the individual intent for each user and items, which is a linear combination by all collective intents. After that, we will get the item individual intent embeddings. Okay, and showing the figure on the right, we first consider the correlation between the interaction and the collective intents, and then construct the individual intents for each user and items. The larger the correlation score of collective intents, the more evidence its impact on users' behavior. Okay. In order to obtain the approximate posterior that can fit the user's performance, we regard the structure embedding we learned and the structure and the individual intent embedding we learned as the variational parameters for the user and item feature distribution. That means we need the mean and the variance. As shown in the figure below, the mean is the structure embedding we learned, which represents the individual performance for user or the individual characteristics for item, and the variance is the linear combination generated by multiple collective intents, which is represented by the back. In fact, after we get the mean and the variance, after we get the mean and the variance, we can get the final feature distribution of user item by the reparameterization trick. And finally, the interaction probability between the user and item is calculated by the inner product, which is also a common practice. Okay. Besides, in order to further enhance the expressive power and deal with the specific issue of implicit feedback, we also resort to the contrastive learning. Specifically, the contrastive learning is to construct different perspectives of the same nodes through the data augmentation. For the recommendation task, we could find that the data augmentation will significantly increase the time complexity for model training, and maybe will corrupt the input data. In fact, the contrastive loss, the influence is the alignment between the positive pairs and the uniformity for the whole feature space. Therefore, we regard the contrastive process as a regularization on the interaction graph. Therefore, the graph contrastive regularization in both interaction and the intent spaces are shown in the figure below. For the interaction space, we have the interaction regularization IR and the homogeneous node regularization HNR for user and item respectively. Specifically, for the interaction regularization IR, considering the recommendation task is to calculate the user item similarity. So therefore, the interaction regularization is a direct GCR process between the user and the positive interaction is most likely least pairwise loss. And we get the uniformity mini-bench. Besides, we also need to prevent the learner embedding from concentrating one direction, which will result in the dimensional collapse. Therefore, the homogeneous node regularization HN try to keep nodes themselves and the positive pairs while keeping different nodes far away from each other. That it means we input the same time of the nodes themselves, and the input to get the alignments is a perfect alignment and the uniformity between among the different between the different nodes. Okay. For the intent space, we also have bilateral intent regularization (BIR) for user and item respectively. Intent indicates different motivation for user's choice. If intent can be represented by others, then such intent may be redundant. Therefore, the bilateral intent regularization try to reduce the redundancy between the different individual intents, which is the same as the homogeneous node regularization. Okay. It should be noted that the G0 process in dual spaces is not independent, but cross-influence each other because we use the representation trick to get the final user or item feature distributions. For example, if we need to calculate the interaction regularization IR in the interaction space, we also need to input the individual intent embedding learned from the intent space and the inputs. Okay. In section 3, in order to verify the effectiveness of BIGCF, we perform experiments on 3 real-world and classic data sets. Specifically, is partial experiments showing there. In order to for the comparison experiments, we choose the baseline, including the MF and the generative models such as the MountVE and the GSIN-based method like GSIN, and the intent modeling based such as DCCF, and the CL-based method called the SGL, and the intent plus CL-based method called the DCCF. And obviously, the BIGCF which is the best performance across the data sets to demonstrate effectiveness. Besides, we also present the comparison about time complexity between the BIGCF and other intent modeling-based methods. Specifically, the time complexity of BIGCF mainly comes from the graph structure embedding, encoding, and the intent modeling process. Since the intent modeling says BIGCF is independent of the number of GCN error and does not require any additional operation for data augmentation. So the time complexity of BIGCF is much lower than traditional intent modeling methods. Okay. Besides, in order to verify the effectiveness of the proposed BIGCF can deal with the specific issue, we also subset the testing set into 3 subsets based on the interaction scale, named the sparsity, norm, and the popular. And the experiment results are shown in the figure on the right about the large GSIN, DCCF, and the BIGCF. And the blue bar is the experimental results of the BIGCF. It can be seen that BIGCF achieves improvements on all testing subsets. And the distributional advantage and gradually increase the gap on specific groups, which indicates that the BIGCF has a better specific resistance. Okay, finally, we present a case study about the individual and collective intents. Specifically, we randomly select a user and realize his correlation score for all 64 collective intents before, during, and after training. It's during the figure A. It can be seen that before training is the blue line. All the collective intents show has the same contribution that cannot distinguish the user's performance. And during training is the orange line. Some aspects that the user care about get larger correlation scores. After training is the green line. The main intent for this user is the C14. It's the biggest one. And the individual intent for this user may come from a collective linear combination, may come from the collective intent C14, C34, and the C45. Okay. Focus on overall behavior. We randomly select the 5,000 users and plot their means and the variance of all collective intents. And showing the figure B, it can be seen that after training, the figure plots the before during and after training also. After training, the most user demonstrate great variance for collective intents, which indicates that each user focuses on different aspects of the multiple intents. Okay. Finally, we let's conclude. Okay. In this work, we divide the intent behind user item interaction into the collectivity and individuality, and propose the recommendation framework called BIGCF, which focuses on exploring the individuality and collectivity of intents on the interaction graph. Besides, we also propose the graph contrastive regularization in both interaction and intent spaces. We try to regulate the uniformity and alignment on the whole feature space, and without data augmentation. In the future, it maybe could explore the more complexity recommendation, for example, the social knowledge or the social network or knowledge graph-based recommendation system, or the more effective modeling for intelligent modeling to further reduce the time complexity. Okay, that's for our presentation. Thanks for listening.